Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome. This is the third lecture of this week. In the second lecture, we introduce the basic concept of finite element method. Okay, and what was this concept? The concept was, let me start with that slide once again. Yeah, that was the slide. So this is the basic concept of finite element method, right? Now we have a domain problem description, and then the problem is represented through a collection of finite elements. This is called finite element mesh as well, and the process of this discretization, process of representation of domain into finite number of finite elements is called mesh generation. And then these meshes, these elements are the building blocks of this finite element mesh. Then the next step is step 2 is element formulation, means whatever governing equations we have, that governing equations need to be written for each element. That is called element formulation. Okay, and then once that is written for every element, then we need to, once we get these equations at every element level equations, and then those equations need to be assembled, and then after assembling these equations we get the equations for the entire system, and then these equations need to be solved. Okay, we will see the major focus of this course. Most of the time we will be discussing the second part, the element level formulation. Okay, and this element level formulation depends on what kind of problem we are dealing with, what is the governing equations. As mentioned in the last class, for two different class or two different problem, maybe we can use triangular element or quadrilateral element in both the cases, but the element level formula, shape of these elements is one thing, but shape doesn't carry all the information, right? So in both the problem we may have similar shapes of elements, similar kinds of element, say triangle or quadrilateral element, but the formulation will be different. The formulations, element level formulation for one kind of problem, where say for instance in that heat conduction problem, and another say elasticity problem, those are different because their equations are different, field variables are different, right? Degrees of freedoms are different. So most of the time in this course we'll be talking about step 2, element level formulation. Okay, then assembly part, when we this is the theoretical aspects. Most of the time, as I said, the theoretical aspects of this course will cover this part, the element level formulation. And then assembling and then solution, the step 2 and step 3, step 3 and step 4, assembling and solution, that will be discussed when we talk about implementation different problems. We'll discuss this too. Okay. And for mesh generation is a completely different field altogether. There are very sophisticated algorithm present, sophisticated software present for this discretization. Okay, now you see, for instance, if we see step 2, for instance, if you take a beam, so suppose this is our 1D bar, and this is subjected to say some loading, some loading P. Okay, and this is say length of the element, this is L, this is x is equal to say 0, and this is x is equal to L, and suppose length is L and the cross section area of the bar is A and Young's modulus of the bar is E. Okay. Now we know that governing equations which describes the behavior of this problem is ddx. We are not going to derive this equation here. Okay. Then du dx. Okay. And that plus b is equal to 0. So this is the governing equation, and then where x belongs to 0 to L. Okay. So x varies between 0 to L. But this information is not complete. We need to the boundary conditions need to be given. The constraint at the boundary needs to be given. And what are the constraints we have? Constraint 1, we have that u at x is equal to 0. X is equal to 0 is equal to 0. That is one constraint. And another constraint we have that you see here it is P, and then the traction at this, if this is cross section area is A and this load is P, then the traction here T bar will be P by A. Okay. So another boundary conditions we have that sigma at L x is equal to L, that is essentially E into du dx, that will be equal to minus T bar. Okay. So this gives a complete equation. This is the boundary value problem for this problem, boundary value problem for this. Now this is the governing equations, and so these equations need to be written for every element. Now suppose if I use finite element here, so this is discretized, the entire bar is now discretized with let us remove the load. Okay, entire bar is now, let us remove the support as well. So entire bar is say represented, say for instance 4 element. So this is element number 1, this is element number 2, and this is element number 3, and this is element number 4. Okay, and this is say node number, this is node number 1. Take note with different color. So these are all nodes. So this is node number 2, this is node number 3, this is node number 4, this is node number 5, this is node number 2. Okay. So if I take element number 1, these different element. So element number 1, 2, 3, 4, and these elements are, this element is node number 1 and 2, these elements connected between node number 2 and 3, this is connected between node number 3 and 4, and then finally this is connected between 4 and 5. Okay, we have boundary conditions specified at node number 1 and boundary conditions specified at node number 5. The node number 1, the displacement is 0, u is equal to 0, and node number 5, the traction is equal to P by A. That is given. That is the constraint we have. And from element number 1 to element number 2, there is a common node which is 2, and through this common node, the information from the continuity from one element to another element is maintained through this common node. Okay. So remember, all these elements are connected at the node. The continuity is maintained through this node. The passing of information is maintained through this node. But now I suggest you to put a star mark here. We'll talk about continuity, completeness in detail in subsequent lecture. Okay, continuity across the element we'll discuss in detail. Now this is the governing equation. This governing equation is valid for the entire domain, and so this also values for every element. So element level formulation, when I say, it means that for every element number 1, 2, 3 and 4, for all these elements, these equations need to be written. Okay. What will be the element level version of this equation? That needs to be written. And once we have written that version for every element, those equations to be combined to get the equations for the entire structure. Okay. Now at this point here I would like to mention another important point. You see, if we take a point in a three-dimensional object, I'm talking about from the context of this problem, elasticity problem. Okay. Now, if I take a point in a three-dimensional object, it has 6 degrees of freedom, right? 3 translation and 3 rotations. Okay. Now, in a two-dimensional plane, we have 2 translation and 1 rotation. Okay. Now, but in this problem, only this is a bar problem. So bar problem means it is again an idealization. The idealization, what is the assumption that the load is the bar is always either axial compression or axial tension. So whatever deformation takes place, that is the axial deformation. So in this case, if you take at every point, degrees of freedom is 1, that is axial deformation in one direction. But then if we look at this bar, it is a collection of infinite number of points. So essentially, in this continuous system, how many degrees of freedom we have? We have infinite degrees of freedom. But then, when we have discretized this system, when we have represented this system into finite number of elements, say in this case 4 elements, and each element having 2 nodes, then the discretized system, after the discretization, after it is subdivided into elements, it no longer has infinite degrees of freedom. See, how many degrees of freedom we have in one element? This is one element. This is one element. So at this point you have, suppose this is node number 1, this node number 2. So at this point you have, say, U1, at this point you have U2. Okay, so U1 is the deformation displacement at node number 1, U2 is the displacement at node number 2, and then this is along the length of the element. So when we similarly, if we take, this is for the single element. Now, if we look at the total discretized structure, how many degrees of freedom? It has 5 nodes. So displacement at 5 points we need to know, and so it has 5 degrees of freedom. So when we have discretized it, then we no longer deal with infinite degrees of freedom. We deal with a finite number of degrees of freedom. And what is that number? That depends on the level of discretization. Now, instead of 5, if we discretize it with 10 elements or 20 elements, my degrees of freedom increases. And if we continuously increase the number of elements, if we continuously increase the degrees of freedom, and then eventually in the limit sense, what will happen? Our degrees of freedom, when it becomes infinite, it will be a true representation of the actual system. Again, I would like you to remind yourself the word approximation. It is an approximation of the actual system. Okay, and this approximation, whether it is acceptable or not, this level of approximation, whether we need to increase the number of elements or not, that when we solve it and get the result, we will see. But this is approximation. If we take the limit, this gives you our actual system. Okay. Now, so taking these equations, as we already now know, finite element method is essentially a technique to solve or to find out approximate solution of partial differential equation, which is the representation of any physical process. Now, from next week onwards, our starting point of our formulation will be these equations. Okay, the governing partial differential equations. And then we'll see how these equations to be written for element wise, and then subsequent assembling and solution. But for some simple system, just to comprehend the philosophy of finite element method as a whole, detailed discussion, as I said, we'll be having in subsequent lecture. Just for the comprehension, let us do some exercise, and the exercise is, you see, for some simple system, we can constitute the element level equations, the element behavior directly without actually starting from the governing equations. See, equations, whatever may be the approach, whether you follow a direct approach or this approach, essentially we are solving the same problem. So essentially we are actually using the same equations, but then approach is different. Okay, just for the comprehension of the entire philosophy, let us take some relatively simpler problem for which the element behavior, element level formulation can be done directly without starting from the governing equations. Okay. So what are and then see what could be the form of that element level information and how to assemble them, and then finally solve it. Okay. Let us take some example. These are some you see some simple cases, mostly in case of bar, so it can be done. So what we do is, we have already taken this example. This is the governing equations, and if we have to do it using finite element formulation, so this will be our approach. We will discuss that later in subsequent classes. Now let us take this example, this problem, and then see how the element level formulation, element behavior can be constructed directly from the basic understanding of the mechanics. Okay. Now, this is important. You see, whatever we do, linear analysis, nonlinear analysis, finite element formulation, or other numerical approach, these are three tenets. These are so fundamental that they need to be satisfied. They may be in the different form, different level of complexity may come in, but these three are very, very important, and even in structural analysis you have used them. Okay. Equilibrium. What is equilibrium? As the name suggests, it maintaining a balance. Maintaining a balance between what? Maintaining a balance between external forces and the internal forces. They should cancel each other. They should balance each other. Okay. That is called equilibrium. And if you remember in structural analysis, you wrote the equilibrium equations, the static equilibrium equations. Summation of forces is equal to 0, summation of moments is equal to 0. Essentially, that is equilibrium. Second thing is compatibility. Compatibility, just for a better comprehension of the compatibility, you can see this animation. The first one is compatible, the deformation. It gives you how the deformation are different parts of the structure or the object related to each other. Okay, this calls compatibility. And compatibility as a word, you know the meaning, and in this context, it has literally the same meaning. Okay, how compatible different deformation and different strains at different points in an object. The first one, suppose as an assembly of four elements, four quadrilateral elements, they are undergoing deformation, and then the first one is a compatible deformation. Okay, and deformation of one element is compatible with deformation of another element, but the second one, deformations are not compatible. When it undergoes, the different elements undergoes deformation, or different parts of the object undergoes deformation, it creates some voids in the object. But please note, if you are modeling fracture, crack propagation, fragmentation, material separation, those are different things. Those discontinuity we take in the equations. Okay, those are taken care of. So this is compatibility. And another, so first gives you how the forces or stresses are related among each other. The second gives you how the displacements or strains are related among each other. And the third one, the constitutive relation, it tells you how the forces and displacements are related to each other, how the stress and strains are related to each other. That is compatibility. For instance, that is constitutive relation. For instance, for a linear elastic material, Hooke's law tells us that our stress is equal to Young's modulus into strain. So that is the constitutive relation. Okay. So this gives you how the stress and strain are related to each other. So these three equations are important, and these three equations are the fundamental. We need to satisfy. Okay. Okay. So next, what we do is, so our problem will be something like this. Problem will be, say, for instance, this is a bar, and this is subjected to, say, the cantilever, and this is subjected to some load, say P. So this is our problem. Okay, and as I said, we can divide it into, we can divide them into smaller segment like this. Now what we will be doing is to write the element level information without starting from the equation, just from the concept of this equilibrium, compatibility and constitutive relation, Hooke's law in this case. Can we write the element level information directly, and that's why this approach is called direct approach. Okay, so let us do that. So take one element, so which is the building blocks of which are the building blocks of this entire domain. So this element has say two nodes. The nodes we are using, say, use red color for nodes, two nodes. Okay, and suppose this is node number 1 and this is node number 2, and suppose this is element E, any arbitrary element E. So what are the degrees of, and we know that suppose length of this element is LE, and area of this element is AE. Okay, E are superscripts. Okay, now what are the degrees of freedom? So degrees of freedom we have is at this point. So at this point we have say this is U1 for element E, and then F1 for element E, the forces, the nodal force. Similarly here also we have U2 for element E, and then F2 for element E. So this is the element. Okay, now just in this context it is of relevance to mention, suppose it is not an actual bar, it is a bar but oriented in a different way. Suppose it is now orientation is horizontal, and we know that always the deformation along the axial direction, therefore we have only U1 and U2 along the length of the element. But had it been like this, had it been an arbitrary shape like this, for instance arbitrary shape like this, and these are the elements, okay, and so this is your node number 1, this is node number 2, and this is element. In that case then you have both the components. So you have a component which is U element 1, it is 1x, and then F element 1x. Similarly here you have, say, U element 1y and F element 1y. 1 is because it is at the node number 1. Similarly here you have U2xe and F2xe, and this will be U2ye and F2ye. So there at every node you will be having these displacement components. Okay, but let us, for the timing, let us concentrate on this configuration. Now the first is the, when we say equilibrium needs to be satisfied, equilibrium at every point needs to be satisfied. So equilibrium at every element level needs to be satisfied. And what this equilibrium tells us? Equilibrium tells us that the forces, summation of the forces should be equal to 0. So F1 plus F2E, this should be equal to 0. Right? Now, so this is our equilibrium equation. Okay. Then what is constitutive relation tells us? Constitutive relation tells us the stress in this element. If we take any point, the stress sigma in this element E will be Young's modulus into epsilon into E. Epsilon is the strain in this element. And what is strain in this element? The strain in this element will be delta E divided by L E, or we are using capital L. So let us take capital L E. Okay. So this will be the strain. Right. Now what will be delta E? Delta E will be delta E. If you look at this node number 1 moves in this direction with U1, and node number 2 moves in this direction U2. So delta E will be U2E minus U1E. That will be delta E. And what will be sigma E? Sigma E will be, now before we write the expression for sigma E, now let us see what is, let us take a section and draw the free body diagram of this element. And if I take a section here and draw the free body diagram of that, this will be something like this. Okay. So this will be your node number 1, this will be node number 1. So here this is node number 1, this is node number 2. So here we have, say, here we have F1E, here we have F2E, and then we have here in this point, that is the internal force, that is PE, and in this case internal force PE, element level. Now you see, let us once again revisit the sign convention. You have already done it. You have already used similar sign convention in your analysis, structural analysis course. You see, this internal force, when say tension or compression, that depends on whether it is, for instance, in this case, the way the force, the stress, the P is shown here, this is tension. Okay. Away from the point, outward from the point, we assume, we use the notion that it is tension. But then when we do algebraic manipulation, when we add forces should not be based on the notion. Forces should be added or subtracted will be based on their direction. Okay. For instance, we know what is sagging moment and hogging moment. During bending, if it is bent like this, we call them, it is a sagging moment. If it is bent like this, we call them, these moments are hogging moments. General convention is sagging moment is considered as a positive moment and hogging moment is considered as a negative moment. But this positive and negative, when you see, it is just to understand the nature of the moment. Okay. But when we add on when we do algebraic manipulation between moments, then this needs to be based on whether it is clockwise or anti-clockwise, right? So the addition and subtraction should be based on that. Okay. So if we from this diagram, from this, we can say that F2E is equal to, from this F2E is equal to our PE, P into E. And therefore, P into A, which is again will be equal to A into E into sigma into E, area into stress, right? So now we are almost done. So this is our now from this expression, if we write. So this is the definition of stress, right? Then what next we can do? So PE we can write as, say, F2E. If we write the expression of stress is equal to this. If we substitute stress is equal to this gives you AE into EE into epsilon E. Okay, and this comes from the constitutive relation, the Hooke's law in this case. And then if we substitute the definition of strain is here, and then this gives you F2E is equal to AE EE into EE will be this, and delta E we already have seen U2 minus E1. So this gives you U2 minus E1 divided by LE. Okay. Now, so this is an important expression. This is an important expression. Now, this expression can be now written as F2E is equal to U2E minus U1E, and this will be K into E, where K is equal to AE EE divided by LE, and this is called stiffness of this element, right? Now, similarly, so what we can do next is, so F2E we have written like this, F2E now KE into U2 minus U1E, right? Now, from the equilibrium equation we know that F2E is equal to minus F1E. So, therefore, F1E will be KE into U1E minus U2E. Now, if we define a vector as F1E and F2E, which is the nodal force vector, F1 and F2 are the nodal forces, right? These are the forces that differ in node. F1E is at node number 1, F2E is the node number 2. This is 2. And if we define another vector U1E and U2E, which is called, say, displacement vector, U1E displacement at the node number 1 and U2 is the displacement at the node number 2, then from these two we can write the equation as this. This will be K into KE, then minus KE, this KE or KE. This is now the element level expression. So this can also be expressed as Fe is equal to, this is the stiffness of this element Ke, and this is the Ue. This is the element level formulation. Element level equation. Element level equation, right? Now, to get this equation, we can get this equation just whatever knowledge we have, the solid mechanics or structural analysis knowledge we have, and we computed this equation directly from these laws, from equilibrium, compatibility and constitutive law. Now, this same thing, now we have several elements now, same thing, element number 1, element number 2, for instance, if this is the problem once again, and if I divide the problem into 4 parts, this is our element number 1, 2, 3, 4. Similarly, we need to determine what is similar kind of formulation, like F1 is equal to K1 U1, then F2 is K2 U2, F3 is equal to K3 U3, and F4 is equal to K4 U4. Okay, and all these are for different elements. Once we have these elements, the equations for each element, next step is to assemble these equations, to combine these equations to get the global equation, the equations of the entire system. Okay, that will give you the now before that, just if we substitute expression of K in this expression of k, we have already seen that expression of k is this. Ke is equal to AE EE divided by LE, and if you substitute that here, then you will see that your KE will be, the expression for KE will be A (1 minus 1 minus 1 1). And you recall your structural analysis, you have already seen this equation, okay, for bar problem or for truss, which is whose orientation is along the axis direction, okay. But if it is orientation is different and you have 2 degrees of freedom at different nodes, then it will be different. So next class what we do is, next class we'll see, we'll take this example forward and then see how once we have this element level formulation, how to assemble them to get the global formulation for the entire system, and then finally solve it. And this is called direct. This is a direct approach. Directly we can compute the element level equations because it's a very simple system. But the same luxury we do not have for all the problems generally we come across, okay. In those cases, this exercise what we have done here now directly, this exercise needs to be done in a different way, starting from the governing equation of the problem, right? Okay, so let us stop here today. So see you in the next class.